And we're back with our shell method. So we've cleared out all that messiness before, all those disks, those washers, and now we're gonna figure out how to do the same volume by using the shell method. And so again, this comes in handy when we can't solve for one of the variables in terms of the other one. We can't solve for the x in terms of the y in order to get the cross-sectional area that we're looking for. And so in this example, you absolutely can do it, so it's kind of redundant. But suppose you had actually something like y is equal to x cubed minus x plus 2 or something like this. If I tell you the y, can you uniquely determine the x for me? It's not quite so easy. So we would like to have a way to do this. But in this example, y is equal to x cubed minus x plus 3 or whatever. If I know the x, I definitely know the y. So if I stop at some particular point x here, I can get a y value. And so that's suggesting to me that maybe I'd like to get an integral in terms of x. I'd like to let x vary and add stuff up as I go and get the area that way, because I can actually find the y values in terms of x's. So let's see if we can do that. So bounds of integration, and we're going to again piece the integral together bit by bit. Bounds of integration are going to be the same. This is particular to this case, though. It's not always going to be the case that the integration in terms of y is the same as the integration in terms of x. You have to solve for the points of intersection of the function. Here, that just happens to work out that way. I should point that out. And as we go from 0 to 1, we're going to stop. This is always the process that we use. We stop at a particular point and say, okay, what is the cross-sectional slice kind of thingy that we get? So we stop here at this point. This is the slice, and when we spin this around the y-axis, as we are going to do, because we're looking for the volume of the solid that we get when we spin this whole banana thing around the y-axis, well, if I spin this around, I'm going to get this thing here, and then this thing there. I end up with this thing that we call, and I don't know why this is happening, this thing that we call a shell. So it's kind of like a tube, and I honestly have no idea why these things are just going away. Again, I have really, really mixed feelings about this program. This Procreate thing is great. You can draw nice colors and do all sorts of things, and it has a lot of great features. And then it randomly will just turn your pen into an eraser and delete the thing that you just drew 3 times in a row for no reason. I don't know why, if it's a cruel joke by the developers or something. I have no clue. So sorry about that. But yeah, what were we doing? Yes, we were finding volumes with shells. So I get this thing. This is my cross-sectional thingy, my cross-sectional volume, this shell, and now I'm giving it this infinitesimal width, which is now dx. I'm stopping into point x and saying, okay, I'll give it this infinitesimal dx width, and these are the things that I'm summing. So I'm doing the sum from 0 to 1 of all of these thingies that I get, these shells. And so what do I have to find? The same way in the washer method, I had the dy, then I had to find the area of the thing at that particular point y. Here, I'm going to be stopping at an x and trying to find the area of the tube thingy that is getting broadened by this amount, this infinitesimal width dx. I'm trying to find the area of that kind of band that we have. And so the way that I do that is I sort of think about actually what it is. Well, it's kind of like taking a circle, and again, I'm not, these are kind of ovals because I'm drawing it in perspective. It's not exactly a top view, but the actual thing is a perfect circle because we're spinning it around an axis. So I kind of take this circle, and this circle, what does it have? It has a circumference. And the circumference, if this is the radius, the circumference is 2 times pi times the radius. So I have that already. This is a circumference, which is 2 pi r. And then I'm going to do 2 things to it. I'm going to sort of extend it up into the second dimension, and this is too big. Let me get rid of that. I'm going to sort of extend it up like this into the second dimension. So now it becomes two-dimensional, and it gains a height. So I have the 2 pi r, the circumference, which I have to take into account when I'm finding this area. Now I have this height here to worry about. And what is the height going to be? Well, let's wait just a second before we do that. Let's get them both. And the final thing that I do is give it this infinitesimal width, which is the dx, and that kind of drags it into the third dimension, so that I can add up all these infinitesimally thin volumes. But I first of all take care of that dx, that infinitesimal width I need. That always goes in, and I'm using a dx instead of a dy because it is the x values that are varying now. And so what's the second part? I need to put in the circumference. So I can stick in the 2 pi out front because integrals are linear. Again, I can put the 2 pi out front there. But now I need to find the radius of this thing. And that's actually not so hard to do because, well, what is the radius? I stopped at this point here, x, and then spun around the y-axis, and this thing is not drawn to scale. This should be the same distance here. This should be an r, and this should be an r. But the point is the radius of this thing. When I stop and spin it around the x-axis, the around the y-axis, the radius is the x value at that point. So the radius is literally just x. I can just stick an x in there. And what's the last bit? So that takes care of the circumference. Now I need the height. I need the height of this thing. And what is the height? Well, it's the height of this stick, this slice that I started out with. That is going to be the upper function, the value of the upper function here. And it's an eraser again. I just love this. The value of the upper function minus the value of the lower function. So in this case, the upper function is x, and I'm going to subtract x squared from that. That is the height of this thingy. So I stick that back in here, x minus x squared, and that is my integral. That is exactly the integral that's going to give me this area. And of course, this is gonna turn into just 2 pi integral from 0 to 1 of now x squared minus x cubed dx. And this is really easy to integrate. We can use fundamental theorem part 2, anti-differentiate. It's just a polynomial. But again, the process is the important thing. How do I think about this? Again, I'm piecing it together bit by bit. I want to go in the x direction, and so x is varying from 0 to 1. And then what is my slice? Well, the slice, I stop at a particular point x, anywhere along there, and I'm going to get this slice. And now when I spin that thing around, what do I get? Well, I get this object. And these are the things that I'm adding up now. These are the infinitesimal volumes that I'm adding. And so I have to figure out what is that volume. Well, it's the infinitesimal width, this dx, times the area of whatever the thing that I get is, the tube thingy. And I piece that together by saying, okay, well, this is, and maybe I'll use this red. I haven't done red yet, I don't think. This is a circumference, so a radius, which gives me the circumference of the thing, and then the circumference, oh my goodness. The circumference is stretched up by the height, and the height is x minus x squared, which is this thingy, and then the radius gives me the circumference, the radius, which is the 2 pi times r, and the radius, of course, is the x, and so that's where that comes from. And we end up with this thingy here. And again, if you do this, so these are really simple examples. We'll see more complicated ones as we go, and then we're going to throw in stuff like now we're rotating around a line, a vertical line or horizontal line instead of the y-axis. But if we think about this again as just figuring out where the functions intersect one another, so getting the bounds of integration, and then saying what is varying, the x or the y, and then how do I stop at a particular point? When I stop, what is the cross section I get, and what is the infinitesimal object, the infinitesimal volume that I'm adding up? If you just do that, you can literally any functions that they give you, you'll be able to do this, piece it together bit by bit, same process over and over again, and you'll find it almost boring. The more you do, you'll realize I'm just doing the same thing over and over again, and it will become more mundane than it was intimidating. So hopefully this is helpful. By the way, if you'll notice, there are probably a lot more mistakes in these videos than in previous ones. I know I promised that the number of mistakes, or expressed hope at least, that the number of mistakes was going to decrease as I went, and the quality was going to increase. I've completely given up on that because I'm realizing that if I'm too much of a perfectionist about this, I have to do like 20 takes of each video to get them almost mistake-free, and that's just going to be taking way too long, and we won't be able to get enough videos to cover all the content that we need to for the rest of the course. So I'm figuring that kind of sloppier ones where I stop and get annoyed by the eraser switching and weird stuff like that, and background noise, and losing my train of thought because of nonsense like this eraser thingy, that it's better to actually get the content in. And if you guys don't mind bearing with me, we'll be able to cover in the time that we have, hopefully, all the stuff that we need. So okay, that's about it for this one. Next up will be some more complicated examples. I think would be a good idea.